In the next two lessons, we're going to look at ways of measuring enthalpy changes during reactions and look at the various experimental techniques involved. In this lesson, we're going to be looking at how to measure enthalpy changes in a situation where, for example, we're dissolving a salt in water, or where there's a displacement reaction or a neutralization reaction. In the next lesson, we'll look at measuring enthalpy changes where there's a combustion reaction involved. Okay, so in this experiment, what we're going to do is we're going to have a look at a displacement reaction, and the techniques involved here also apply to dissolving or neutralization. Okay, so what we're going to do is look at the reaction between zinc and copper sulfate. So this is a displacement reaction, and the zinc displaces the copper from the copper sulfate solution, forming a clear solution of zinc sulfate, and then copper metal is precipitated during the reaction. So what we're going to do first of all is form a solution of copper sulfate, and to do that I'm going to add 2 grams of copper sulfate crystals to 25 milliliters of water in a polystyrene cup, and then the polystyrene cup is going to be placed inside a glass jar which is filled with some insulating material such as polystyrene, little polystyrene beads or cotton wool or something like that. Okay, and I've also got a lid ready which I'm going to put over the polystyrene cup when I start the experiment, and the thermometer is going to fit through that lid. And so what I want to do is I want to really measure the temperature change that's produced as soon as I add zinc powder to the copper sulfate. And I'm going to use that temperature change to work out the change in enthalpy during the reaction. What I want to ensure though is that when I add the zinc powder to the copper sulfate, that all of the copper is displaced from the copper sulfate, so all of the copper sulfate reacts during the reaction. So I've got to make sure that happens, and before I can do that I've got to work out how many moles of copper sulfate I've got in the solution. So let's have a look at that a minute. To do that we need to know the formula molecular mass for copper sulfate, and well, I've done that for you here. 63.5 for copper, and then sulfur 32, 4 oxygens is 64. That gives us 159.5 grams. We'll just call that 160 grams to keep things simple. And so we want to know how many moles of copper sulfate have I got. Well, we can say 1 mole of copper sulfate weighs 160 grams. Then I added 2 grams, so how many moles weighs 2 grams? Okay, just playing around with that, cross multiplying if you like, you can say that you can see that x will be equal to 2 over 160. So I've got 0.0125 moles of copper sulfate in the solution. So what I want to make sure is that I add a greater number of moles of zinc powder to the solution. So I look at the periodic table and find that my relative atomic mass for zinc is 65 grams. So I've got to add more than 65 times 0.0125 grams of zinc to my copper sulfate solution. That comes out as 0.8125, 0.8 grams, call it. So let's just say what we'll do then is we'll add a gram of zinc. So I want to add surplus zinc powder, so I'll add a gram of zinc to my copper sulfate solution. So the second step is to add 1 gram of zinc powder. Now as soon as I do that, I'm going to stir the solution with the thermometer, which will already be fixed inside the lid. So let's just do that. 1 gram of zinc to the solution. I quickly stir that around. The thermometer is held by the lid, and then what I want to do is measure the temperature change that occurs. And so what is important is during this reaction heat energy is going to be released. That's the change in enthalpy that we're trying to measure, and what I don't want is that heat to escape from this cup. What I really want is all of the heat energy that's released during this reaction to be transferred to the water in the solution to heat up the water in the solution, and then I can use this to measure the energy that's been transferred. We'll look at that step in a minute. So it's very important that this cup is well insulated. You've got a polystyrene cup positioned in a whole load of insulating material with an insulating lid. So I just make a note of this. I added, this was surplus zinc, that was important, and then I measure the maximum temperature rise. Okay, so let's just say I do that, and normally what you do is you plot a graph, and you use the graph to estimate the maximum temperature rise that's produced during the reaction. And let's just say that we find that the maximum temperature rise was 8 degrees Celsius. And that's a typical sort of value for this amount of water and this type of reaction. Okay, so we've got an 8 degrees Celsius temperature rise. That was what was produced by this reaction. Now then, what we're going to do is we're going to use this to work out how much energy was released during the reaction. So we move down a bit, and we're going to calculate the energy released. So we need to know the specific heat of water. And basically, when water is heated, what we can say is that 4,200 joules of energy will raise the temperature of 1 kilogram of water by 1 degrees Celsius. All right? We can state this in a slightly different way by saying that the specific heat of water is 4,200 joules per kilogram per degrees Celsius. Okay, so what we want to do then is work out how much energy was involved in changing the temperature of our mass of water in the beaker by 8 degrees Celsius. So we use the energy specific heat equation. Okay, so that tells us that the energy that's transferred to the water in the beaker, all right, that's the energy that's transferred to this water in the beaker during the reaction, is equal to the mass of water in the beaker multiplied by the specific heat capacity of water, which is 4,200 joules per kilogram per degree Celsius, multiplied by the change in temperature, which was 8 degrees Celsius. So we plug those values in, we find out that the energy is 0.025. So remember, this is really important, that the mass of water is measured in kilograms, not in grams. So we've got 25 milliliters of water, which is equal to 25 grams of water, which is equal to 0.025 kilograms of water. So that's the figure we put into our equation. So 0.025 multiplied by 4,200 multiplied by 8, that's the temperature change, and that gives us 840 joules. Okay, so just summarizing that again, what's happened is then we've added the zinc to the copper sulfate solution. As a result of that, 840 joules of energy was released during that reaction. We're not quite there yet, because remember that the enthalpy change, which is written alongside this reaction, alongside this equation, is the amount of joules which is transferred per mole. What we've done is we've worked out the amount of heat that was transferred when only 0.0125 moles of copper was displaced. So we've just got to do another rule of 3 to work out the total enthalpy change. So as I just said, 0.0125 moles of zinc will displace 0.0125 moles of copper from the copper to sulfate, releasing 840 joules of energy. So the question is, how much energy is released when 1 mole of copper is displaced from the copper sulfate solution? Alright, just play around with that rule of 3 and you'll see that X is equal to 840 joules divided by 0.0125, which equals 67.2 kilojoules. So the enthalpy change for this reaction is equal to, and that should be a minus actually, because, and that should be a minus as well, because energy is being released. It's an exothermic reaction. is minus 67.2 kilojoules per mole. Now the reference book value for the heat of enthalpy for this particular reaction is minus 217 kilojoules per mole. So as you notice, there's quite a large difference between the value we obtained in our experiment and the true value. So you'd normally need to explain this difference. Principally, the reason for this is that there were greater heat losses than you wanted. So this lower figure here is due principally to heat losses from the apparatus that we're losing. We really wanted to contain that heat within the polystyrene cup so that it all got converted into a temperature change in the water, but that didn't happen in reality. Quite a lot of that heat escaped from the cup, so you need to explain, that's the principal reason for why our value for enthalpy change is a lot lower than it should be. Okay, so in the next lesson we'll look at how to measure enthalpy changes for a combustion reaction.